This meeting is being recorded.
In this first video from Chapter 17 on additional aspects of aqueous equilibria, we're going to take a look at some concepts, some topics regarding aqueous equilibria that may not have been addressed in previous chapters. So the first of these concepts is something called the common ion effect. And as the name implies, we're going to be looking at an ion and finding what happens if we have an additional amount of an ion that would form when something ionizes or dissociates, and how that will affect the equilibria. So if you recall, we looked at the Le Chatelier principle earlier in a previous chapter. And we noted that equilibrium can be affected or shifted to the left or the right towards products or reactants, depending on addition in this case, or subtraction also works for shifting, but in this case, addition specifically of a common ion. So we can think about adding an additional product to our equilibrium. So let's take a look at this specific reaction here. Say we have acetic acid, a weak acid, and we add that to water. So we're going to get our equilibrium to establish here. We get our hydronium ions, and then we also get acetate ions. So that's what this looks like here. And say we already have acetate from another source in solution, right? Or if we add acetate after the fact, we would shift our equilibrium towards reactants, and less would ionize, right? More would form our weak acid as we increase this amount of acetate. So if we initially have a common ion to start, if you recall, we can think of our Ka expression as this form here. So we have our concentration of our products over concentration of our reactant on the bottom, the acetic acid. And so if we're increasing the top here, our products are increasing. To keep that equilibrium established at that value, we're going to have to shift it and, in theory, increase the reactant. So that's the why. Let's take a look at how this acts if we have a problem here. So with sample exercise 1, we're going to calculate the pH of a solution that has 0.085 molar nitrous acid, so all that down to here. And we're given the Ka value and also the chemical formula of nitrous acid. So if you recall, this is a weak acid, so hence the Ka value. Since this is so small, this change that will result due to this small equilibrium constant, we'll see that we're actually going to ignore our X value and not have to do the quadratic formula once again. So that's usually good news for students, but let's take a look here at what would happen. I'm writing out the chemical equation at equilibrium here. So we have our nitrous acid, we add it to water, we get our nitrite ion, so that word there. And then we have an additional source of that nitrite ion from this potassium nitrite. So we're given a second concentration here. So 2 concentrations were given, the Ka value, and then our source of the common ion here is going to be the anion nitrate. So how do we set up our ice table? Well, the same way that we would without having any initial common ion. So we would have 0 hydronium here. So the only thing that's going to change is going to be our column with the nitrite. We're going to add our 0.1 molar here to the initial. So we're going to put in that we initially have this over here instead of 0. So we'll make it the same amount of sig figs. And then we have this 0.085 molar over here to start. Our change is going to be exactly the same as we've seen in the past. So we have minus x plus x plus x for all 1-to-1 coefficients. Now let's see what we have at equilibrium. So we have 0.085 minus x. No surprises there. Same way to find our equilibrium concentration. Now, instead of 0 plus x, I'm going to have 0.10 plus x. And then over here, I'm still going to have my x. So let's take a look at if we were to set this equal to our Ka expression, what this would look like. We would have that Ka equals the concentration of products. So we have 0.10 plus x for our concentration of nitrate. Then we have just x over here, and that's going to be over 0.085 minus x. So I mentioned earlier that we have a really small Ka, so 4.5 times 10 to the negative 4. So that would give us a very small change. So not only will this x disappear, but also this x here. So our calculations will be fairly simple, right, without these two x's here. So let's reorganize this equation a little bit. I'm going to rewrite it over here off to the side. So this 4.5 times 10 to the negative 4, this will now be equal to x times 0.1 in the numerator, and then just 0.085 down here. So I'm going to multiply both sides by this value to get rid of that. So my new improved equation, let's make some space down below, will look like this. If I rearrange to solve for x, we're going to have 4.5 times 10 to the negative 4 times 0.085. All right, and now we still have to divide both sides by 0.1 to get rid of that term. So I'm going to now divide over here by 0.1, and that's all equal to x. So if you plug this into your calculator, remember you can ignore that small x. You should get that this x value that we are solving for, that we have to keep, the only x that we keep, this is going to be equal to 3.83 times 10 to the negative 4. And just to remind you, that's this x here, the hydronium ion concentration. So we're asked to find pH. So this would be the value that we use to plug into our pH expression. Remember, that's the negative log of the hydronium ion concentration. So that's what we have here. So 3.83 to the negative 4th power molar for concentration. And we get this is equal to about 3.42.